All right, welcome to the presentation for question 3, Bushy trees. If you have not watched the previous 2 videos on binary search trees, I'd highly recommend watching those first, as those provide a lot of useful context for how binary search trees work. However, without any further ado, let's get into the question itself. So this question is asking us to implement a function called from sorted array for binary search trees. We are given a sorted integer array called array, and then we want to efficiently construct a balanced binary search tree containing every element of the array. For an efficient implementation, try to minimize the runtime of from sorted array while ensuring that the final binary search tree is balanced. And as a hint it gives us, we want to think about setting the median as the root of your binary search tree. Let's also take a moment to look at all the tools that they've given us, right? So we have a definition for a class called binary search tree. Inside this binary search tree, we have a class variable called root, which is a node. And the class node is also defined here. This is a very standard implementation of node. We have a t, which is the value. We also have a node, which is the left subtree as well as the right subtree of this node. Then we have this function, the function we are trying to figure out, right? We have from sorted array, which takes an integer array called values. It creates a binary search tree BST, which is empty at first. And then we're going to populate this binary search tree by setting its root to the return value of this helper function, also called from sorted arrays. And as you can see, into this from sorted arrays, we're passing the values array that we took. We're also passing the number 0 as well as the values at length -1, which are the beginning and end indices of this value, right? And in this function is what we're trying to implement. We're taking an integer array called values, we're taking an integer called lower, and an integer called upper. And if lower is greater than upper, we're going to return null. If not, we're going to create an integer called middle, which is corresponding to the middle index of the array using this equation. Right. So take a moment to think about how you would go about implementing this question. And it's a bit challenging, so give yourself like maybe 5 to 10 minutes to think about just exactly how you would do this. All right, so let's start by considering how we would write our pseudocode for this question? Because for all code writing questions, the first step is kind of understanding what the code we want to write is, right? And so let's think about how a binary search tree works, right? A binary search tree has a parent node, then every single value to the left of that is less than the parent node. Every single value to the right of that is larger than the parent node. And the way we can do this is we'll realize that the middle index is actually corresponding. If we break our array, our large array, into 2 parts around the middle index, then everything in this left half is going to be less than the value at the middle array. Everything in this right half is going to be greater than the value of the middle array, which is kind of exactly what we want for our binary search tree, right? So let's take this idea and kind of run with it, right? Here is my pseudocode. First of all, we want to set the root node equal to the value at the middle index of the array, right? Then we're going to split the array into 2 halves around the middle array. We're going to set the left subtree of the root to the middle index of the left half. Then we're going to repeat this process for the left subtree. This is a recursive function call. Then we're going to set the right subtree of the root to the middle index of the right half. Then we're going to repeat this process for the right subtree. And here's how the implementation would actually work. Right, here's the text, right? So node, we're creating a new node called mid that is currently null. We're going to set mid's value to the value in the values array at the index middle, which we found. Then the way that we actually break apart the values array into 2 halves array is quite smart, right? So we're going to recursively call from sorted array until we are no longer able to. And the way we're going to do that is we're going to change the lower and middle and the upper bounds, right? So in the left half, well, lower stays the same, right? Because the leftmost value of the left half is still going to be the same leftmost value as the entire array. However, the right bound of the left array is instead going to be equal to middle -1. Take a moment to think about why that is true. All right, then mid.right is basically the same thing, right? However, we're going on the right side. And so by setting lower to middle +1, we are basically excluding the middle index and then considering everything to the right of it, right? And when we recursively call this function, we'll see that it creates a binary search tree. Let's take a look at this diagram to kind of understand what exactly is happening here, right? So say that our array is represented by this long line, right? first of all, this is the first thing that we're doing is we're finding the value which is in the exact middle of this, right? Then what we're going to do is we're going to create we're going to break it in half, right? Where this lower, as you can see, the index of this lower stays the same. The index of the upper stays the same. However, because of this gap, we're creating this gap by doing middle -1 and middle +1, right? And then we've broken this array into 2 halves. Then we're going to find the middle of this again, and we're repeating this function recursively now, right? So once again, we're going to break it in half, and then we're going to create more. And if we repeated this, we would see, this pattern repeated over and over again. And so when we draw the connections like this, you can see, voila, we have created a binary search tree, right? And the reason why this is work, this follows all the properties of a binary search tree, right? Because every single value on the left here is going to be less than the value at this node. And then everything left of this node is going to be less than this node, right? And that is exactly how a binary search tree works.